Welcome back, everyone. We are in 4.35 talking about something called Probit regression. So the basic idea of this section is to try to expand the set of models that we use to capture the posterior probabilities on classes. And so we're going to talk about this Probit model here, and we'll discuss where it can come from. So how you might encounter it in the data. So we'll talk about one way where you can think of the outputs being 1 or 0 based on whether the input is greater than some threshold, but then the threshold itself is noisy. And we'll talk about that and how it gives rise to the Probit model. I'll also talk about, I'll add something on is seeing this Probit model as how taking your data, adding some noise to it, and then comparing that to a fixed threshold. So just a slightly different view on the same model, but might be a bit more intuitive and maybe more applicable. And then we'll just talk about how we come up with this Probit function, and then figuring out what its weights are, which is just, we don't talk about that too much. It's just the maximum likelihood. And then at the end we'll actually compare it a little bit. There's kind of an interesting comparison of how these two models talk about outliers. So the Probit model and the logistic model, we'll talk about that. And finally there'll be a little bit at the very end on how to deal with mislabeling of data, which can certainly happen in real data sets, and it's kind of a nice way of dealing with it probabilistically. So we'll just talk briefly at the end about how to deal with that. Okay, cool. So let's just talk about Probit regression. Okay, so we've seen for a broad range of class conditional densities. So remember that was like the probability of x given ck, described by the exponential family, the resulting posterior class probabilities. So the p of ck given x. Are given by logistic transformation acting on a linear function of the feature variables. However, not all choices of class conditional density give rise to such a simple form for the posterior probabilities. And in real life, you certainly aren't going to have these aren't going to be necessarily well behaved, right? So for instance, if the class conditional densities are modeled using Gaussian mixtures, right, there's no reason to think that it's going to come out looking so nice. So this suggests that it might be worth exploring other types of discriminative probabilistic model. Okay, but we're going to keep things simple here. We're in the two-class case, and again, remain within the framework of generalized linear models. So we're going to just simplify things a bit, but give you some exposure to a slightly different type of density. Okay, so that the probability of the posterior probability on a label being 1, given the inputs, is going to be some function. So there's the activation function of some linear function of the features or the inputs. Okay, so we're going to motivate this. So one way to motivate an alternative choice for the link function, we're going to talk about this noisy threshold model. Okay, and so it says for each input, we're going to take, we're going to evaluate this drive, and now we're going to set the value according to, so it's going to be 1 if a of n is greater than theta, and 0 otherwise. Okay, so far so good. So just doing kind of a threshold comparison. But if the value of theta is drawn from a probability density, so I think I need to really highlight this. That's the key point. So theta itself is kind of moving around. Then the corresponding activation function will be given by the cumulative distribution, so and so, right? So this is just going to be the probability. This is capturing the probability that this is basically the probability that theta is less than or equal to a, right? Because the total probability of that, because that's what's going to give us a 1, right? So if a is greater than theta, that means theta is less than or equal to a, and that's this quantity here, integrating from minus infinity to a. Okay. So now let's use a particular example of this. So suppose the density is given by 0 mean unit various Gaussian. So we just plug that in for p of theta. So you've got your inputs coming in. There's this threshold that's just hovering around 0, just moving around all the time. So this particular version is called the Probit function. Sigmoidal shape, you can look it up. It looks basically like it has a sigmoid. It looks very similar to the logistic, but it actually has one crucial difference at the end, which I'm glad he pointed out. Because I didn't know that, and I think it's quite a useful one. A sigmoidal shape, and it's compared with the logistic sigmoid function in figure 4.9. Now note, okay, so don't let the use of a more general Gaussian distribution does not change the model, because it's equivalent to rescaling of the linear coefficients, right? So it just says, for example, if you want to change like the standard deviation, and you made it equal to like some sigma, well then it's exactly the same model as having 1, but now we scale the weights down by sigma, etc. So this is quite general as it is. Okay, so now do we get this Probit function? Typically not, but we have a closely related function called the error function, which you might have seen. So this is integrating the Gaussian, the standard Gaussian from 0 to a, and they're related. So that's kind of how you go from one to the other. The generalized linear model based on a Probit activation function is known as Probit regression. So if you if your situation is one like this, where the outputs are potentially generated, by this noisy threshold, this might be the model for you. Also, yeah, we can determine the parameters of this model using maximum likelihood. And in practice, the results found using Probit regression tend to be similar to those of logistic regression, except for a couple of cases that we're going to talk about momentarily. One thing I wanted to point out was that you can, as I said, you can motivate this model slightly differently. So again, we're going to just start with and I'm going to drop the n. So imagine you just have one observation. So now instead of comparing this to a noisy threshold, we're going to make actually a random variable b, which is going to be a plus z, and z is some noise, and z is going to be distributed according to some probability of z. And then we're going to say, well, t is equal to 1 if b is greater than or equal to 0. Okay, so our threshold is just 0. So now, well, then this is this will happen if and only if a plus z is greater than or equal to 0. Which will happen if and only if z is greater than or equal to minus a. Okay, and then we're kind of in the same situation as we were when we were introducing the Probit model. So now this is going to be, and so the probability of this is, okay, so it's going to be from minus a, so that's the probability of z greater than or equal to a is equal to, minus a. Right, of course. Okay, but now so now we're going to assume some additional things. We didn't have to assume them before. Let's assume that z is symmetric. So it's a Gaussian. That's fine. It'll be symmetric. Not everything will be. Like if you had like a gamma distribution, it wouldn't be. But let's just work with a symmetric distribution. Well, then this is going to be. We can just change variables to that, right? So this is going to be from minus infinity. Oops. No, so this is going to be from a to minus infinity of p of, I'm just going to abuse some notation here. And additionally, so we're going to assume that it's symmetric. So then this is going to equal to minus, so p of z, and so that's the minuses come out here. This is due to symmetry. P of z dz of a minus infinity, and if we got a minus on the integral, that's just going to be the same as swapping the order of integration. Okay, so this model that we just introduced, at least for symmetric distributions on the threshold, can just be, you can motivate it exactly the same way as just taking your input, adding noise to it, and comparing that to a threshold. So that might be kind of a bit more, it might be a bit more applicable to you, but as you can see, they're kind of just two sides of the same coin. Okay, so just another way of thinking about where the probit might come around. So the probit's going to come around if that noise is Gaussian. So you can imagine, for example, the input to a neuron, which is, okay, it's got some drive, but on top of that, there's some noise sitting on top of it. Okay, so now the probability of activation is going to be, again, a probit function, because now you have a noisy signal being compared to a threshold, to a fixed threshold. Although neurons, do they have thresholds? And the thresholds certainly won't necessarily be fixed, etc. But in a simplified setting. Okay, so that's that. So now one issue that can, so let's move on. So one issue that can arise in practical applications is that of outliers. So this is a big deal. Let's highlight it. Okay, for instance, through errors in measuring the input vector x, or through mislabeling the target value t. So we're going to talk about the second one in the next paragraph, but let's talk about the first. So because such points can lie a long way to the wrong side of the ideal decision boundary, they can seriously distort the classifier. And remember, we already saw this when we were talking about using least squares to do classification versus logistic regression. Least squares was very sensitive to outliers because those, the farther out the points were from the decision boundary, they would affect it would affect the loss quadratically. So the farther you are, the things get really bad, and so the decision boundary moves to accommodate those few guys outside rather than most of your data which lives maybe closer to the boundary. So they can seriously destroy the classifier. And now this is a key distinction between the probit and the logistic. So note that the logistic and probit regression models have behaved differently in this respect. So this is cool. Because the tails of the logistic models decay sigmoidally, whereas for probit activation, they decay with exponential and quadratically. So exponentially to the minus x versus exponentially to the minus x squared. And so the probit model can be significantly more sensitive to outliers. And so the reason why is that under that model, the farther you are from the decision boundary, things should be going down quadratically. So it does not expect to find points that are far from the decision boundary. So if there are actually points far from your decision boundary, it's going to move the boundary to accommodate them. And then you'll have those guys determining the boundary rather than the bulk of your points. Whereas the logistic function has exponential decays, so it's a bit more forgiving of, says, okay, yeah, there is some probability, it's not going to zero that quickly. Okay, so most of our points can live here. There can be the occasional guy, farther out, and it won't move the boundary too much. So that's what makes the logistic model more robust to outliers than the Probit model. Okay, and you might have heard about like things like robust regression. It's exactly the same idea, where instead of using like the squared error, you just use the absolute value of the error. So that kind of allows more, allows you to accommodate outliers a bit more readily and not be so swayed by them. What kind of similar ideas? Okay, and finally we've got this how to deal with mislabeling, and the probabilistic approaches gives you a very natural way to deal with this. So that's however both the logistic and Probit models assume the data is correctly labeled. The effect of mislabeling is easily incorporated into a probabilistic model by introducing a probability epsilon. So let's just highlight that. That the target value has been flipped to the wrong value, leading to a target value distribution of this form. So it looks like, so if it hasn't been flipped, then your probability of t is going to be your normal one. Otherwise, with some flip probability, it's going to be 1 minus sigma, 1 minus what you had, right? And you can just combine it, obviously this way. So if you want to be like extra, extra detailed about it, you can write this as the probability of t given x is the probability of t correct. Let's call it correct. Given got to sum over this, and let's just sum over correct. That's the best way of doing it. Let's just write it this way: probability of t correct given x plus p t not correct given x, right? And this is going to be probability of t given correct x times p correct plus p t given not correct x times p not correct, right? And so then, so this is your epsilon. This is 1 minus epsilon. Oops, nope, the other way around. This is 1 minus epsilon. This is epsilon. Probability of t correct. Well, this is just the label is correct, so it's just your standard form. And then this would just be 1 minus the probability of the correct one, right? Because so this would actually be it would actually be this probability of not t, right? Because you got to flip it, and that would be so that would mean that because not t would be the correct value, and this would be 1 minus sigma of x, because normally sigma of x predicts the 1 value, not the 0 value. So anyway, just spelling that out in some detail, but I think it's relatively clear from that example, from those expressions anyway. Cool. Okay, so I think that's all I wanted to say about Probit regression. So I think it was cool. Just you're not always going to get logistic functions popping out. There's some very natural settings where you wouldn't. One of them is a setting of the noisy threshold, or the noise added to the signal for a fixed threshold, and that's where you see the Probit function. I thought it was very cool to point this out, that the logistic function is less sensitive to outliers because of these decays. So I think that's I'm going to put an arrow there because I think that's a very important point to be aware of. And then how to just incorporate mislabeling is very nice in the probabilistic approach. It's just very simple, allows you to deal with it in a very easy and principled way. Excellent. So hope you enjoyed that. As always, just let me know if you did or you didn't, and I will see you next time when we will talk about how all of these different pieces, well, except for the Probit one, I think, but how many of them can be derived from as members of one big family. So we'll talk to you then.